if you check the screen, let me just go back to the previous lecture. But the other class I have discussed two properties, right? This was the one property jahan pe I'm saying that the rank will remain the same if you add two tensors of, let's say, rank 3, it will remain as 3. That was one property. The second property was also very simple. It is something which we call as outer product. So if you have two tensors, one of rank 3, one of rank 2, and you are multiplying them, you'll get a new tensor which will be of order 5. Okay, this is called outer product. We are going to look into one more property which we actually call contraction of tensor. Okay, contraction of tensor. This is interesting when we do it. So contraction of tensor, what happens here is, if you have a tensor of rank 5, it can actually reduce to a tensor of rank 3, but that will happen if you know mm, base is repeated, or this contravariant, it may be a mixed tensor. Okay, any of these basis vector is getting repeated, we will actually have that contraction of tensor. So it is going to look into that now. So the topic is contraction of tensor. So let's just write down one tensor. Let's say a p q r s t, right? So we have seen this. Okay, there are different ways of writing it. Today I was actually looking into a video and I saw that this guy has written it in a different way. So how many are there? 5. So that means there should be 5 numerator and 5 denominator which are multiplied with each other, right? So what we can do is we can just simply write it down as del x. थोड़ा space देके लिखना चाहिए, but so everything is del x here. Del x, so we can just write down directly del x, del x, del x. ये भी और एक आ गया. So we have to write down del x's. Okay, done. And then we have got pqr in the numerator, so we can just write down p here, q here, r here. St is at the denominator, so we can write down s and t, and it will be all in the s dash frame, s prime frame. So I'll put a bar here, यहाँ पे, यहाँ पे, यहाँ पे. So done with this, and then we have to just fill out with I. Right? So I can write down xi, xj, xk. Anyway you write, you can remember it. That's more important. यहाँ पे l, यहाँ पे m. These are not bars, right? So please remember this. Okay, I think I've written too small, but write down del x bar, del x bar p divided by del xi, then rq के साथ j, r के साथ k, l के साथ s, m के साथ t, and that's it. And then you have already defined these, so that means it all will be in terms of I, j, k, l, m. So I, j, k, l, m, right? So if you write down an expression this way, we can actually write it down in this form, not a problem. And then I said contraction of tensor. So I said if a basis vector is repeated, so if p, q, r, s, t, so let's just repeat one basis vector. Let's say if r is equal to t. So I'm repeating, right? So you see, you have got a t here, and then you have got the r here. So that means these two, maybe I will just use a different color. These two I will separate out. This is one, and this is two. So let's separate them out and write the remaining ones together. Okay. So what I can do is I can simply write it down as, okay, this is a bar. Okay, the bar रहेगा ना इस side को. This is in S dash frame. This is in S frame. Okay, so this is P, Q, and then I'm saying R is equal to T. So let me just repeat R here. S और T की जगह लिखेंगे R. So we'll just write down R. So we have this, and then I can again do the same thing. I'll write down del X divided by del X. Now this is I've already written, so it's easy. P, and then this is I, and then it is del X bar Q, and then del X. You have to just practice it once or twice very slowly, and then I think we should be able to do it. So you have written 2, this one is left, so I'll just write down this also, del XL bar del XS. यहाँ पे खाली mix up नहीं करना है, important, sorry, this is L not bar, S के साथ bar है ना, this is L, this one. Yeah, so this is done, and then let's write down the remaining terms in the bracket. So bracket, we'll write it down as del x bar r divided by del xk into del xm divided by del x bar. I will t ki jagah r is equal to t, so t I'll replace it with r, so I'll just write down r here. So straight away you see that this term and this term will actually cancel out, and you will get del xm by del xk, and this is actually nothing but the definition of Kronecker delta. Okay, and that is the thing that we are going to do now. So I'll write it down as a I j k l m. ये तो सेम रहेगा, right? So therefore what we can do is we can write it down as a bar p q r s r is equal to, this is getting repeated, so that means it is going to be a tensor of rank 3. अगर rank 3 here, we are going to get 3 differential terms, so this term automatically goes out because it becomes Kronecker delta, right? So let me just write it down quick. Divided by del xi into del x bar q into del xj into del xl divided by del x bar s into delta mk. M is at the numerator, k is at the denominator, so in Kronecker delta also we use the same sequence mk. So this is Kronecker delta a I j k l m, right? If you go for the definition of Kronecker delta, we know that del m of k is equal to 1 if m is equal to k, is equal to 0 if m is not equal to k. So if m is not equal to k, तो झमेला ही खत्म, everything becomes 0, but that is not the aim, right? M is equal to k, this will become 1. Okay, so I can actually combine m and k. So if I do that, I can simply write down this expression as when, let me write down when m is equal to k, so we can just write it down as a bar p q r s r is equal to this and this, del x bar p del x bar q del xl del xi del xj del x bar s. Done. This is m is equal to k, so k m both will be so delta is equal to 1, m is equal to 1, so this is just 1, let me not write it down, and this one I can write it down as a I j k. Okay, and at the bottom it will be again l and k. So what do we observe here is that this k is actually getting repeated, right? So that means k is repeated. Don't write this down, I'm just explaining it. In exam you don't need to write down such thing, right? Therefore order is 3. So order is determined only by the non-repeated term. So I is not repeated 1, j is not repeated 2, l is not repeated 3. So order is 3. This side also it is p, q and s, r is repeated, so order is 3 on both sides. So what we see that a tensor of rank 5 will be now a tensor of rank 3 if one of the basis vector is repeated, right? So reduced, maybe you can write down reduced from rank 5 to rank 3, right? So that is why it is called contraction of tensor. Hence maybe I can just write it down this way. You can also write it down this way, okay, it's fine, no problem. Contraction of tensor. So this is also a property. So you know all these properties are very obvious if you know the basic definition of tensor. That's it. Once you know the basic definition, you really don't need to look into the tensors. Okay, so you really just need to know the properties, and it's very simple. Okay. I have one more property, but here I'm not going to do it. I'll just leave it to you. So if I just want to do it, number 4. Okay, so yesterday I've given you outer product, today I'm going to tell you about inner product, but here I'm not going to do anything, you can do it on your own. Okay, it's very simple. The idea is that first you do outer product and then you do contraction. Okay, number one is outer product. You do outer product, and number two you do contraction. So when we talk about contraction, what we do, we actually have a order 5 tensor or order 3 tensor. We repeat one value and it will reduce by 2 orders, right? So that is what is contraction. And what is outer product? We have already done it yesterday. So this I'll leave it to you. Outer product. See, I've taken this. This is the fifth order tensor, and I will get this. I'll get this. So once I get these, then I can actually maybe I can repeat PQS RT. I can replace this. Let's say T is equal to S, and then I can repeat it. And then here it will be L and M will become equal, and then this will also be a third order tensor. This will also be a third order tensor. So that is called inner product. So in one word it is called inner product. In general it is nothing but you take an outer product, then you do a contraction, you will actually say something which is called inner product. It's the same thing, so I'm not repeating it. Okay, this is also a property. So if you know the other two, the third one or the fourth one is actually easy. Okay, so that's the property of tensors. Okay, today I'm going to just give you two more theorems which are very simple. So in a way, you know, when you start with tensor you feel that okay, this might be a difficult unit, but let me tell you, this is actually easy and you can score good here in this particular unit. Okay, why? I'll give you one example now only. I am going to solve a problem and you'll see that this is actually very simple. Okay, this is something which is called the symmetric and antisymmetric tensor. We have already seen the definition, so let's just try to understand it better. ठीक है, so अभी जो हम लोग टॉपिक लेने वाले हैं वो है symmetric and anti-symmetric. So yesterday we have already seen, okay, anti-symmetric tensor. I've already given you a definition. If you want to define it also you can do it, but then it's not very complicated. So symmetric क्या होता है? If you take, let's say, Aij may be a contravariant tensor, it will be same as Aji. It's not necessarily a second order tensor, maybe a third order also. Okay, or maybe if it's covariant, I can write down this as Ij is equal to Aji. Okay, so this is an example. This is just repeating. Okay, we yesterday already told you symmetric. And anti-symmetric, maybe I can take it as Aji, Iij is equal to minus Aji. So this is anti-symmetric. And yesterday I think I've given you one more example. I can also have something like A, P, Q, R, S, T. If I interchange the position of two basis vector at a time, I can write it down as minus A, P, R, Q, maybe S, T. Okay, so this is minus. So these are all examples of symmetric and antisymmetric tensor. Now based on this, there are certain proofs that we can actually work on. Okay, so let me just write down one question here, okay, which will be interesting. Let me take one example. Okay, so you can say it's a kind of theorem. Okay, we're just going to prove it. Okay, so prove that a symmetric, or it may be a covariant or a contravariant. Okay, covariant tensor of second order. Now we are all comfortable with these terms. Okay, so it's not difficult. Has, okay, this is something which I have to write. Independent. I'll give you a basic definition and then I'll progress with the proof of this. Component in n dimensional, let's say v to the base n. Okay, so what is this actually? This is something which we have to prove. Independent component. So if you write down, let's say, something in the matrix form, you know how many component it has. Okay, so in that way, so it is n into n plus 1 divided by 2, independent component in n dimensional space Vn. Okay, so this is what you have to prove. But then It seems to be very complicated jargons and all, so that's why I'm just going to give you a note first, and then we are going to progress. This note you don't need to include, you just need to use it for understanding purpose. So let me say I have got a symmetric tensor. That means I have got a I j is equal to a j I. Okay, somehow I don't like the red color. Okay, so we have this. Now if we are basically considering see, okay, this is there, that means we are talking about a symmetric tensor, okay, in 3D space. So it's a three-dimensional space, 3D space. So there are two basis vectors. That means it's a tensor. If there was only one basis vector, it would have been a vector. So there will be 3 square, which is equal to 9 components, right? Why 2? Because it's I and j. It was a k, then 3 cubed, right, and so on. So you can write down anything in terms of that, okay? Representation is important. So if you just want to write down all the components, let's say, how will you write it down? So I have, let's say, 1 1 a 1 2. This is actually something which is represented. This is a representative form, not necessarily a matrix, but obviously it looks like a matrix. It is how we represent it, that's it. And this would be a 2 1 a 2 2 a 2 3 a 3 1 a 3 2 a 3 3. So as soon as I say 9 component, where are those 9 components? These are the 9 components. So A11 is one component, A12 is one component, and so on. Okay, and if you remember, we have done before, we have written it as, you know, you have a space S where you have got x1, x square, x cubed, and so on. So these A11, A12, these are all functions. These are functions of x to the power 1, x to the power 2, x to the power 3, and so on. Okay, but then they will actually represent a tensor. This entire combination will represent the tensor, which will define the entire system. So that's how we use it. Okay, so this might represent a moment of inertia. It depends on what kind of tensor or what kind of space you are considering. Okay, but let's not get it complicated. Let's just say that this is how we are representing these 9 components. Now the question is, how many independent components are there? Let's check. First thing is total component, which is equal to 9, that we can see, right? And then, you know, these components are not getting repeated. Okay, let me take a different color. This one is there, a11, a12 or 21, a22, sorry, a33. So a11, a22, a33, there is no repetition. So these are all independent components for sure. So we have got in the, this is for understanding. Okay, just copy this, you'll understand this. Independent component is equal to 3. So there are 3 independent components. Other than that, we are also having these components, a12, a13, a23, a21, a32, a31. Now these are all forming in the upper triangular matrix and the lower triangular matrix, right? And the property is already given that aij is equal to aji, because we are talking about a symmetric tensor. Why we are studying symmetric? Because the question says symmetric. So if it is antisymmetric, the properties will be kind of different. So we're not going to look into that right now. So that means that what we can do here is, let me take a different color. A12 is equal to A21, A13 is equal to A31, and finally A23 is equal to A32. So these are, you know, repeated. So that means there are 3 independent components, and from here also we are actually getting 3 independent components, right? 3 independent components, because it's getting repeated. So the repeated ones are not obviously counted, common sense, right? We're just taking the 3. So that means total independent components. Independent, remember the term. Total independent component is equal to 3. These 3 plus, okay, color code. Let's use color code. 3 plus 3. Which is that 3? These 3. And these 3 are from here. Okay, so that's there is equal to 6. So there are 6 independent components. So I've just taken a 3 by 3 form. Okay, I've just taken 9 components, but here it is an n dimensional space. So how many components will be there? There will be n square components, right? It is an n dimensional space. 3 by 3, 3 square. Okay, it will be an n by n, so it will be n square. So this is the idea that we are going to use to prove this. So this is the note that let's all of us remember. Let's go to the proof. Okay, so we will go to the proof now. So I will copy this. Okay, so we're going to prove this, right? So this is what we have to prove.
Sir, hello sir.
Yeah, yeah. Tell
So
me.
the last two lines, can you please repeat again?
Okay, I'll just repeat it. Just wait. Go to the previous slide. So this is my question. If you go back here, uh, you want to know this about this the total independent components, right? So what happens here is you have got the independent components. That means it is repeated. A11, A22, A33. These are not repeated. So these are three independent component. We are already saying it's a symmetric tensor. That means aij is equal to aji. In general, a12 would be a21, a22 would be a13 would be a31, and a23 would be a32. So these are all same. This is same to this. This is same as this. This is same as this. So that means they will represent just three independent components because the other three are a repetition because it's a symmetric tensor. So that means the total independent component would be this three plus this three. So what happens is we are basically considering a 3 by 3 form. So that means there are 9 components. What is the space? 3D space. How many basis vector? 2. So that means it is 3 square, which is 9. Now it's an n dimensional space. It is not 3 dimensional space. It's an n dimensional space. Okay, and that means that if I write down the vector form, matrix form, you will get n square components, just like this. Okay, so I'm going to show you this. Okay, let me just write down that vector form. I think then it will be more easy. Okay, so forget about what I have said. Let me write down it and just you have a visual information here. Okay, so how do I solve this? So since I'm solving a problem here, let me just write it down in a way you should be able to write it in exam. That's very important. Okay, let's write down the solution. So let aij, okay, we are taking only two basis vector. Okay, don't consider it to be n number of basis vector is 2, but we are considering a 3, not a 3 dimensional space. We are considering an n dimensional space, so we can have n combinations. Okay, so you're going to see what exactly I mean by that. So let aij are component of a symmetric covariant tensor of second order. Okay, so that's it. Okay, and since we are saying it's symmetric, we have to mention this is very important. Then aij is equal to aji. Okay, but then this is actually valid for all values of I and j. So it may be 1 2 3 and 4 and so on. Okay, it will be valid for any value of I and j, so that is important. So let's just write down that in the representation we have just now shown. So first term would be a11, then it will be a12, then it will be a13, and so on. How many? N, because it's an n dimensional space. It was 3 dimensional, so we stopped at 3. It is n dimensional, so it is a1n. Next we'll go for a21, a22, a23. We just stopped at a23, which was 3 dimensional space. It's n dimension, so it is a 2n. Now this side it's a square matrix form, right? It is n, that means this side also it should be n number of values. In 3 dimension we went up to 3 1 3 2 3 3, that's it. But here we will go from up to n. So it will be a n1, a n2, a n3, and square matrix. So we'll stop at a n n. That's it. Right. Now if you want to measure how many terms are there, okay, total component, it's obviously n square, because this side there are n terms, this side there are n terms, so it will be n into n, which is n square, right? So you can see this, right? 3 by 3, it will be 3 this side, 3 this side, so it will be 9. Here also it is n this side, n this side, so it is n square. So if I want to write down the total component, this is actually a very easy derivation if you understood what I said in the last slide. Total component is equal to n square. Okay, and then if we look into the repeated index, that means we are having 1 1, 2 2, 3 3, 4 4, and so on up to a and n. So there will be obviously n number of terms with a repeated index. Okay, so let me just write down this number of components with repeated index. By repeated I mean 1 1, 2 2, and so on. Okay, with repeated index. Okay, we have this as equal to n. Take a different color. Is equal to n. Okay, so this is with repeated index. That means we are talking about a diagonal component. Diagonal component. Okay, that's it. Now we have got number of components. Okay, now I'll tell you this number of components of distinct index. That means 1 2 1 3 3 4 and so on. Okay, 3 3, I mean, okay, so DINCT distinct index. Now this I have to determine how many would be there. See, A12 is A21, A13 is A31, correct? So that means if we go into this previous section, you have total component 9, independent component with repeated index is 3. So number of distinct component would be nothing but whatever is the total, which is 9, minus independent component with repeated index, that is 3. So that is equal to 6. That is how you find out the components which is distinct, right? Symmetric tensor. So here also number of components of distinct index, total component is n square, and you just subtract it with this. So I will take minus n. Okay, so you have to check this. See, 6. Which are those 6? 1 2 3 4 5 6. Total n square. I have subtracted the number we have at the diagonal and I get the other components. So that is, we have got n square minus n. But what we saw in the previous section, that obviously it's 6, but then it's getting repeated. That means whatever is the number, we divide it by 2. If it is 6, we are getting 3 independent components because all of them are getting repeated. So that means if you want to find out the total component, it will be 6 divided by 2, which is 3. This is this 3. So here also we are going to use the same logic. Okay, without looking into the property of symmetry, we can actually find it out. So what we can write down is number of components reduced to, therefore number of independent components is equal to n square minus n, the total components with distinct index, but they are getting repeated, so we are going to divide it by 2, n square minus n by 2. So this derivation that we are doing is more or less logical. Okay, we have to just understand this. So we have got number of independent components here, n square minus n by 2. Total number of component was n square, and the total number of component with repeated index is n. So this is independent repeated index, this is independent component, and this is the effective independent component when we are considering the the symmetric property. So that means if we add these two, we are going to get the total number of independent components. obviously, right? So therefore, okay, therefore total number of independent components is equal to, diagonally there are n distinct elements, so it is n plus independent component. When we are considering the other term is n square minus n, but the problem is it's a symmetric property, so term gets repeated, so we will just divide it by 2. So if I do the LCM, this is 2n plus n square minus n divided by 2. So this is n plus n square divided by 2, which is equal to, take n common, this is n plus 1 divided by 2 proved. So whatever we have done in the previous classes on tensor, we have more or less understood the basic. We know what are the terms, what does it mean, what does independent means. Today something which you have seen. We know what do you mean by second order. We also understand what do you mean by, the importance of dimension. We know what is symmetric tensor, covariant we know, that's why I've written it at the base. So if I give you a question, prove that a symmetric contravariant tensor, there you will write down ij at the superscript and not the subscript. Don't miss that out. If you write it down at the subscript, I'll give you 0, because it means that you don't remember the difference between covariant and contravariant representation. Okay, so representations are different. So even if I talk about a contravariant also, you are going to get the same result. You're going to do it in a similar way. The answer will be same, n in 10 plus 1 divided by 2. Please check this. This is second order. That's why we are just considering I and j. If it was third order, I would have taken it as I, j and k, and accordingly these would have changed. So if I want to represent, a third order, see, this is complicated. We have a tensor, it's a second order, it's very easy to represent. It's two dimensional. One is this, one is this. If I want to represent it in a third order, we have to take this matrix, and below that we have to write another matrix, and so on. Okay, I'll just give you an example here, maybe. Okay, इसको रहने देते, इतना ही अच्छा लग रहा है. So if you know it's a basically a third order, how will you represent it? Although I'm not going to ask you any questions for that, rest assured. Okay, but I'll just want to make this clarification here, that why tensors and metrics are not the same thing. It can be a combination of metrics, but not the same thing. So if I write down a third order, you may write it down as this. Okay, you have one term here, a1 1 1, start with this. Okay, and so on. Even I'll get confused there, I know. So you have got one matrix here, one matrix here, and at this also you are going to write down. So this is a 3 by 3 matrix. There at the bottom you will again get a 3 by 3 matrix, and then again you will write down a 3 by 3 matrix. How many terms here? 9. How many terms here? 9. How many terms here? 9. So you're going to write down 3 by 3 matrix here, 3 by 3 matrix here, 3 by 3 matrix here, one below the other, not one by the side of the other, one below the other. You consider a three-dimensional image. Okay, so it will be something like this. You have got one 3 by 3 matrix here, and below that you will be having one more 3 by 3 matrix here, and below that I'm going to have one more 3 by 3 matrix here, and this will actually represent that tensor. There will be 9 plus 9 plus 9 components, which is equal to 27. So that means if I am considering a matrix or tensor in third order, okay, sorry, in three-dimensional space, and it is basically a third order tensor, it will be 3 to the power 3, which is 27. Where are those components? These are written like this. I'm not going to ask you any question on this. I just declare you this beforehand. Okay, but then I hope you understand the importance or the difference, basic difference between a matrix representation and a tensor representation. It's kind of different. Okay, okay, one last thing I'd like to do today is another question. Okay, let's just check this out. Okay, let me just write it down anyway. So the question is, show that, okay, if a tensor is symmetric, if a tensor is symmetric, So these small terms plays a very important role. Symmetric, so I know what property I should use. Okay, in one coordinate system, it is symmetric in every other coordinate system. Every other coordinate system. So I think let me not solve it now. I'll give you this question, not exactly as a homework. Okay, it's like you have to just think about it and try doing it. You can get it in any book, mathematical physics book, not a problem. But then understand the logic here, that if it is symmetric in one coordinate system, it will also be symmetric in another coordinate system. So if you actually represent this, I'll give you a hint. Aij bar, you can write down it in terms of the transformation equation. Maybe I can write it down as mn. Okay, and I can just reverse this and I will know it will remain the same. Okay, and if it is symmetric, it means that a m n will be equal to a n m. So whatever was here first term, second term, in terms of m and n, I can interchange them and write it down as n and m, and I will see both of them will remain same. So that means aij will be equal to aji. Okay, so anyway, I'm going to give you a detailed proof tomorrow, but I'm not doing it. I just want you to think. Just write down this question, think about it, okay, and try to do it. It's actually a two-line answer. Okay, it probably will be a 2 marks question, not beyond that. It's a very short idea. Okay, it is something like, if you have done matrices meticulously, okay, some properties and all, probably this one also you'd be able to do. Okay, it's not at all complicated. Ready to pair. Okay, so that's very important. Menu on your device. Bluetooth is on. Just a sec.